exploration. All right, so we're going to spend most of our time this week just on this one section here. And this, I mean, there's entire classes that can probably be taught just in EDA. I mean, in fact, I'm sure that there are. All right, but we're going to hit some of the highlights, and especially as it relates to prepping our data in order to get it ready for machine learning applications. All right, so there's some pretty standardized, I think, items that we think about when we move into this phase. And again, this is in alignment with this 4+1 model that we've talked about. But and there's a lot of depth here, but we're going to hit some of the highlights. We're going to talk about basic variable types, which we've done already, but we're going to talk about kind of the functional types associated with, what are the data frames, things we're going to build. Anyway, I don't have to go through all of these, but as you can read through this list, you can see that, this is a pretty big topic here, all right, that could be covered for, multiple weeks. So we're going to move through some of this pretty quickly, and especially as it relates, like I said, to kind of getting our data ready for machine learning applications. All right. So I think of these as variable types, all right, as compared to data types. We talked about data types kind of in exhaustion the last couple of weeks, but we're going to use all of these moving forward, all right? And so especially especially data frames, all right? We get very familiar with data frames, and we're going to do a lot of lists as well, all right? So lists are compositions of one type of data type, data object, all right? Sometimes you can combine them, but for the most part, they consist of just one type of data type, all right? And then data frames are going to be this is going to be when we load our data in, all right? It's our two-dimensional data objects. They're going to have all sorts of multiple variable types, all right? So that's strings, objects, all right, complex numbers, whatever that might be. And that's going to be important because remember, as we move through our operations and getting our data prepped, we have to make sure we keep a clear eye on what are our data types that we're using and make sure that our variables are in the right one, all right? We also are going to be using matrices a lot, especially for more of our complex machine learning operations. And that's going to require us to convert most of our variables, all of our variables, into some type of numeric form. And so we're going to cover some of that today as well. So a lot of it's going to be moving from a data frame to a matrix, all right, as it relates to kind of using more complex measures. We're not even complex, really. We use anything that has a distance component, all right, if we're trying to measure how far apart two variables are. That all has to be in numeric form. So we'll talk about how to do that. And we can do that with our categorical variables too, by turning them into dummies or one-hot encoding them, making them zeros and ones as compared to just lists of different categories, all right, nested in one column. All right, so these are some fun or useful, all right, functions that you can use right at the get, okay? So X in this situation, all right, is going to represent the data that we have loaded in, almost certainly going to be a data frame. We're going to use pandas, and these are all pandas functions. The info one, we're going to use a ton, all right? And that's going to tell us everything from data types to the size of the data set, to the number of missing values. It's really very helpful, all right? Shape is going to give us the dimensions. Data types is specifically going to tell us the data types that are in each one of the columns. And then describe gives us a whole bunch of summary statistics, all right? Now, what I would recommend is go ahead and opening up VS Code, loading in any data set. You can even use previous code from some of the other examples that we've used. Load that in and then give these functions a try, all right? So just replace the name of the data set that you have loaded in, whatever you called it, with X here, and all of these functions will work, and you can look at the different information that they're going to give you. So this is important stuff to do right off the get once we load in our data frames to better understand exactly what we're working with, all right? So prevalence, we're going to talk about a lot. It's kind of like a baseline. All right, so this is specific to classification problems in particular, all right, and it's the proportion of a particular population found in the positive class. What that means is, as an example, if we're working on a target variable, we're trying to train an algorithm to predict whether someone will default to a loan or not. This is like a pretty typical example used, all right? In this example, the prevalence would be the number of people in that particular data set that have defaulted on their loans, right? So that could be anywhere from 70-30, right? So it might be like just 30 people, out of 100. Sorry, I'm writing this really clunky. 30 people out of 100 have defaulted on their loan. And so the prevalence in that particular example would be 30%, all right? And this is important to know because it kind of tells us how hard that particular target variable is going to be to learn. All right. Now you can imagine if, say, this number moved to like 95 to 5%, right? So that's only 5% of the total people in that data set defaulted on their loan. Understanding the patterns of those 5% as compared to the 95% is going to be can be very difficult. All right. And that might mean that we need to have a lot of data, or we might have to reshape the data that we have to give the algorithm more information about that 5%. Right, but we have to know that up front. So we want to do that. We want to understand our target variable and just get an idea about what that looks like. All right, so that's an important other thing to understand, especially as it relates to classification, which is what we're going to spend most of the time on in class. All right. All right, scaling, normalizing, and one-hot encoding. All right, scaling and normalizing can be kind of seen in the same vein, or they're converting numeric numbers, right, into some standardized format. And maybe you've heard of z-scores or something like that you've used in the past. That's an example of standardization. All right. For what we're going to do in this class, we're much more likely to probably use a min-max scaler, right, where we put all the numeric variables between 0 and 1. And this is really important because, especially as an example, and we're going to show it in KNN, this is kind of a distance-based measure. We want those scales to be the same so that the distances between any two variables are on the same standard scale. All right. You can imagine if, for instance, we were comparing weight and height of two individuals, a weight can vary significantly, up over, 300 pounds, right? Whereas height generally does not have this large numerical variance. All right. So trying to compare the space between those two variables would be very difficult unless we normalized it, right? Because we put both those variables on a scale between 0 and 1. So you're going to need to do that. Okay. This one here too for logical, right? This is the idea is that we would create individual columns for each of the factor variables or categorical variables that we have in our data set. All right. So if we had, a category, just to make it totally generic, or just a color category that had three different variables in it, it was either orange, three different levels, like orange, red, or green. Instead of having them nested in one column, we would split those out, where a 0 would be present if that particular row was an orange, or was or was not an orange. It would be 0. All right. If, say, it was a red, then there might be a 1 underneath red, and then there'd be a 0 underneath purple. I mean, that's probably a pretty bad example, but the idea here is that you have these different levels of categorical variables, right? So wherever instead of having them nested in one column, right? So if we had them nested here, like 1, 2, 3, all right? So instead of having nested under this, what we would do is we have individual columns for each one. And I'll show you this in class, right? So we basically split these out so into individual columns, all right? And then it's just a 0 or 1 underneath each one of these, depending on whether they happen to be that row falls into that particular class. All right, so this would be like a 0 here, maybe a 0 here. This is a kind of a terrible example again, and this would be a 0 here. So this column would be a 1, this column would be a 2, and then this column would be a 3. All right. Anyway, like I said, we'll go over that a little bit more in class. But again, the idea is to turn those categorical variables into numeric. All right. I talked about the min-max scaler. All right. There's entire books that have been written on just how to handle missing data. All right. So we'll confront this a lot. There'll be some missing data in your lab as well. You'll have to figure out exactly how to deal with that. All right. So Python comes with a bunch of packages and functions that can handle missing data. But the key that we want to try and discover, all right, and we'll talk about this, is to understand if there is, a pattern to that missing data, or is it completely at random. All right. So now if there's a pattern, it's important to know that, right? Because it could be information about how we could potentially replace that missing data. All right. If there appears to be no pattern at all, if those variable missingness is not correlated with any other variable, etc., that's probably a better scenario. All right. Then we can kind of handle exactly how to deal with that random missingness. But if there's a pattern, that means there is some information inside that data set about why those missing values are there, and we got to figure that out. All right. Otherwise, we're kind of going into building our algorithms a bit blind. All right. A good way to start out, just to get just to get up and running to see how much missing data is just, again, to use this info function, all right? And it'll tell us it'll tell us in a printout there exactly how many values are missing in each variable. So it kind of gives you a chance to discover patterns as well, right? So we see 2 variables or 3 variables or 4 variables that all have the exact same number of missing values. Usually that's an indicator that there's some pattern, and we got to better understand that, all right? As a general metric, if we have more than 5 or 10% of missing values, we really got to take a look at that and see what's going on in any one column and develop a plan. And the plan might be to delete that variable, or it might be to reduce the entire size of the data set, to limit it to the total non-missing values in that particular category. Those are 2, blunt approaches. And there also could be some choices about how we do imputation, which is how we replace those missing values with other values like the mean. All right. Okay. We're also going to have to do partitioning and sampling. All right. So a foundational concept of machine learning is how we do this training, tuning, and test data sets. And what that involves is dividing our data set into 3 partitions. One that's fairly large, which is probably the training set. That might be 80% of the data. And then 2 smaller data sets, all right, used for tuning and test, all right? So tuning is a way that we can modify our algorithm, whether that is the hyperparameters, right? Remember, the hyperparameters are the particular features of an algorithm that can be adjusted, or we do data engineering, right? Which are the actual variables that are going into the model. We might change those, and then seeing how that affects the performance of the model. All right, so we do all sorts of things in the training and tuning phase to try and optimize its performance. And when we think it's totally done, we think we've got a really good model going based off the back and forth between training and tuning data set. And I'll show you how to do this. And then our very last step is to push in that test data set to get a final validation on how things worked. All right. The concept behind this is that what we want to do is have an independent sample, right? That wasn't used in the training process at all right, to test and see how the model's working, right? It's kind of like an independent test example. There's lots of different ways to do that. One of the main ways, and this is the sklearn package or scikit-learn, is through this function called train test split. All right, and I'll show you how to do that. And we're also going to need to do stratified sampling. All right, stratified sampling means that we're going to split the data set based off essentially the prevalence in the target variable. All right, so we want the same amount percentage-wise of information to go into the tune, the test, and the training set as it relates to that target variable. Again, just to go back to the example we had, if we had a 70-30 split, right, we want 70-30 split of that training to go into the training set, all right, to go into the tune set, and to go in the test set. We want the 70-30, that ratio, to show up in each one of these partitions. It would be a problem, as an example, if we had, say that shifted to, 90% to 10%, right, in the test set, all right, then when we went to go and test to see how well we've trained it, it might not work that well, right, because we don't have a representative sample of what we actually trained the data on. So that's an important thing to keep in mind. That's why we do stratified sampling. All right, we'll talk a little bit more about that. All right, so cross-validation is a concept I'm just going to introduce, all right, that we're going to show up a little bit later. It's kind of a stretch concept. The idea here, all right, is that what you do is you take that training set, all right, and you divide it further into multiple partitions and train multiple models and then average those together, all right, to create a more robust model as compared to creating just one test set, right, and just one training set, all right? So what this does is it allows us to use the power of sampling. We're going to go back and sample that training data set multiple times, build multiple models, all right, and then average those out to help us better understand how the model's working in a more robust way on that training set, all right? So this is an example here, all right? So where we might take the train set and we divide it into essentially 4 parts, right? So here, this would be the first part, right? And so what we might do here is that the model would get trained on this partition of the data and then just tested on this fourth of it. And then here, it would get tested on this one, trained, I'm sorry, on these 3 partitions and then tested on this kind of, I don't know, was that third quartile. And then here you can see, it's just what we do is essentially remove a fourth of the data every time, right? That does not overlap with the fourth of the data that got removed before. And then you just average all of these models together, all right, to create a more robust output, all right, as compared to just doing one large training and then testing data set, all right? Because no matter what you do, if you add more data to the training, you're going to take it away from the test. That's why this kind of tug of war rope is represented here, because they steal from each other. But here's a little bit more of a robust way to handle that. All right. And we'll talk more about that. As we move forward with the class, we're going to be our default way for training some of these methods, train some of these models. But I just want to introduce that right at the beginning. Okay. So that's phase 2. We're going to move into phase 3. All right. Next week and the week after, we're going to keep touching on these topics every week. So don't think this is the only time all this is going to show up. This phase is a expansive area, all right, of the machine learning life cycle. We're going to go into it in great detail throughout the semester, and more things. We're going to add more stuff to this. This is just like a quick overview of some of the topics that we're going to be covering in this week. But again, there'll be more things that we add into there, and you'll get practice using those over and over again. And then next week, we're going to go into things that are much more specific to kind of model building, all right, in particular, all right. We introduced this a little bit about the difference between hyperparameters and parameters, but all these topics here really have to do with specifically the training process in particular, whereas what we're looking at here is kind of more like prepping the data in order to get it ready for training, all right. So that's where we're at, and I will see everybody in class.